In last video, we began discussing eigenvalues and eigenvectors. So this time we'll see more examples and study the question of when there is a basis of eigenvectors. A quick recap from previous video: if a linear transformation from V to V is, for example, phi is Rn and T is given by the matrix, and T acting on vector V is equal to lambda V, then V is said to be an eigenvector of T with eigenvalue lambda. And the eigenvalues can be determined by solving the characteristic equation. So determinant of T minus lambda I, lambda 1 is equal to 0. The eigenvectors for the given eigenvalue lambda can be determined by finding the kernel of matrix T minus lambda I by row reduction. So if V is the basis for V, which consists of eigenvectors of matrix T, then the matrix TB is a diagonal matrix. Now, if V is equal to Rn, the n-dimensional Euclidean space, then matrix T is the matrix of T in the standard basis E1 through En, and the matrix B formed by columns of vectors B1 through Bn which are the basis vectors. Then the matrix of linear transformation in that basis script B is equal to regular B inverse T times B. So in other words, a square matrix M, this matrix can be written as X times diagonal matrix times X inverse, exactly when there is a basis of eigenvectors script B of M. In which case we just take X to be formed by columns of the basis vectors. This is good for computing powers of M, right? So M to the N. So first you need to switch to the basis where M is diagonal, compute the nth power of the diagonal matrix there, which is just, again, simply computing the powers of the diagonal entries, and then switch back to the original basis, and then therefore the Mn is equal to X times this diagonal matrix to the power N times X inverse. Note that the notions of eigenvectors and eigenvalues, like this, they only depend on the matrix T and not on the choice of the basis where we wrote T in. So the way we write down the eigenvectors does depend on the basis, right? After all, we are presenting them as linear combination of basis vectors. However, the characteristic polynomial, but the eigenvalues, they do not, right? So, and if you make a change of basis, this matrix B, then a change of basis always amounts to this transformation here, and we can you do the following simple algebraic manipulation. So the determinant of M minus lambda 1 is equal to determinant of B inverse times, so we can multiply by B inverse from the left and from the right, and because the determinant has a cyclic property, right? So we can multiply by B minus 1 here and by B there. It will be an identity transformation. And then we can put it in, so it's equal to determinant of B inverse MB minus lambda. So take a matrix 0, 1, 1, 0. Its characteristic equation is determinant of matrix negative lambda 1, 1 minus lambda is equal to 0, which is equal to lambda squared minus 1. So its eigenvalues are 1 and minus 1. The eigenvector for the first eigenvalue is the kernel of this matrix, which is spanned by vector 1, 1. And the eigenvalue for the vector -1 is the kernel of this matrix, which is formed by 1, -1. This is the basis of real eigenvectors. And so all coefficients are real. So later in the next video, we'll talk about complex eigenvalues and eigenvectors. Take a matrix like this. So it has 1 in every row and column, 0, 1, 0, 0, 0, 1, 1, 0, 0. Its characteristic equation is now a determinant of a 3 by 3 matrix like that. But the star formula of the calculation of the determinant gives us the simple cubic polynomial, which has one real solution, lambda equals 1. But there are also complex solutions. We'll talk about them later. So eigenvector for the real solution 1 is the kernel, is formed of the kernel of this matrix. And you can check that if you take 1, 1, 1, it annihilates it, right? This matrix acting on vector 1, 1, 1, 1 gives 0. Okay. So, but since there's only one eigenvalue, and we clearly know that it's a 3-dimensional space, right? So there is no basis of real eigenvectors. Consider matrix 0, 1, -1, 0. Its characteristic equation is this, right? It's a lambda squared plus 1 equals 0. And then it has no real solutions. So there is no real eigenvalues whatsoever, or non-zero eigenvectors. And it has no real eigenvectors. Take matrix 1, 1, 0, 1. Characteristic equation is lambda squared minus 2 plus 1. So you can complete the square. It will be equal to lambda minus 1 squared. So there's one eigenvalue, lambda equals 1, but it appears twice in a sense, right? So the eigenvectors for this eigenvalue are the kernel of this matrix, and this is spanned by 1, 0. And that's it. So clearly in this case also there is no basis of real eigenvectors because, well, we need 2 vectors to form a basis in 2-dimensional space. So this example is, let's do one more example. Now let's take the identity matrix 1, 0, 0, 1. Its characteristic equation reads, again, the same. 1 minus lambda squared equals 0. So again, eigenvalue is equal to lambda, and eigenvectors for eigenvalue 1 is the kernel of this matrix 0, 0, 0, and it's any vector in R2. So in this case, there is a basis of real eigenvectors. Okay, so here, that's right. Now, well, let's keep doing examples. Take the linear transformation, which is the derivative, right? So it's the which acts in the space of polynomials degree up to n to itself by differentiating each polynomial. The constant polynomials are eigenvectors of eigenvalue 0. And there are no others, right? So the derivative lowers the degree of a polynomial. So any eigenvector must have eigenvalue 0, hence be a constant. Now, or we can pick a basis, say 1, x, x squared, etc., in the space of polynomials. We can write the matrix of d over dx. So let's write it for in case of P4. You can see here that, well, because of the way derivative works, it would differentiate it would put down the power, right? So it's the derivative of x to the 4th, it will be 4x cubed, right? So therefore you need to write the number 4 here. Derivative of x cubed is 3x squared, and derivative of x squared is 3x, 2x, and derivative of x is equal to 1. So we have these numbers above the main diagonal. Sometimes it's called super diagonal. And if you write the characteristic polynomial of this equation, you'll put sort of, it'll be this matrix minus lambda times 1, and you get equation negative lambda 5 is equal to 0. So 0 is the only eigenvalue. And the corresponding eigenspace is this basis, right? It's spanned by 1, 0, 0, 0, right? It's the only thing, which are the constant polynomials. So proportional to vector 1 in this basis. So we saw a bunch of examples when there is no the basis of eigenvectors, and we saw examples when there is a basis of eigenvectors. So there's a theorem. So let T be a linear transformation from V to itself, and suppose that V1 through Vn are non-zero eigenvectors. So that T acting on Vi is equal to lambda I times Vi. If the eigenvalues are distinct, then the eigenvectors are linearly independent. Let's prove it. First, check for n equals to 2. Assume V1 and V2 are linearly dependent. So there is a non-trivial linear combination of those vectors with coefficient C1 and C2, which are both non-zero. Let's apply vector operation T to this linear combination. And because V1 and V2 are eigenvectors, we have this equal to lambda 1 C1 times V1 plus lambda 2 C2 V2 is equal to 0 as well. So if C1 is equal to 0, we know that C2 is not equal to 0, so we have to conclude that V2 is a zero vector, which is a contradiction because we assumed in the beginning that they are non-zero. So C1 is non-zero, and then if lambda 2 is 0, right, then we have that lambda 1 C1 V1 is equal to 0, but we know that lambda 1 is not equal to 0, so therefore lambda 1 is not equal to lambda 2. Then since C1 is not equal to 0, we have V1 is equal to 0, which is again a contradiction. Otherwise we just subtract 1 over lambda 2 times the second equation from the first to find that C1 times 1 minus lambda 1 over lambda 2 V1 is equal to 0. And since lambda 1 is not equal to lambda 2, this implies either V1 is equal to 0 or V1 is equal to 0, which is a contradiction. So we have exhausted all the possibilities, having assumed in the beginning that the two vectors are linearly dependent, and it failed, right? So therefore, it is impossible, and vectors V1 and V2 have to be linearly independent. Now, so more generally, you consider a minimal dependent subset of those vectors. There must be at least 2, since Vi was non-zero. So each of those vectors was non-zero. And then we can put 0 equals sum of Ci times Vi, where all Ci's are not equal to 0 by minimality considerations. And then for notational convenience, we assume that V1 is just among them. If not, we can just relabel. Now we can apply T, and then we'll get 0 equals sum Ci lambda I Vi. By minimality, none of those lambdas can be 0. But then we can subtract lambda 1 times the first equation from the second to get this thing above, this thing below. So sum of all over all i's bigger than 1, Ci times lambda I minus lambda 1 times 1 has to be non-trivial. And then since the eigenvalues are distinct, so lambda I is not equal to lambda 1, then the linear combination of fewer, we got a linear combination of fewer of the basis vectors. And that's not minimal. That contradicts the minimality assumption that we had. So let's prove the theorem. Now there's another theorem. Let T be a linear transformation from V to itself. And suppose V1 and Vn are less than 0 eigenvectors. So if the eigenvalues are distinct, then eigenvectors are linearly independent. That's the theorem. And the corollary is that if the characteristic equation of an n by n matrix has n distinct real solutions, then there is a basis of real eigenvectors. Now, it is not a necessary condition. It is sufficient, but not necessary. So the identity matrix has a characteristic equation 1 minus lambda to the n, which has only one real solution, lambda equals to 1. But any basis is a basis of eigenvectors for the identity matrix. And because it's simply x by every vector with multiplicity 1. So if T from V to V is a linear transformation and lambda is an eigenvalue, then we say that the kernel of matrix T minus lambda times I, in other words, the space which is spanned by the eigenvectors with eigenvalue lambda, is the eigenspace of eigenvalue lambda, right? So it's the kernel, the null space of this matrix, T minus lambda I. Example, take matrix 1, 2, 2 on the diagonal. So its eigenvalues are 1 and 2. You can check that. So the eigenspace for the eigenvalue 1 is spanned by E1. And the eigenspace for eigenvalue 2 is spanned by E2 and E3. So they live in the kernel of this matrix minus the eigenvalue times times the identity matrix, right? Because when you subtract identity matrix from here, you get times 2, right? You get a minus 1, 0, 0, and then therefore any linear combination of the 2 and 3 will be annihilated by this matrix, and same thing works here. Now, one can show, although the proof due to the time constraints will be beyond the scope of our class, that for linear transformation T from V to itself, the following statements are equivalent. So first, there is a basis for V consisting of eigenvalues for T, eigenvectors for T. The eigenspaces of T span vector space V. And then the eigenspace of eigenvalue lambda has dimension equal to the multiplicity of lambda as a root of the characteristic polynomial. So in particular, in that example with the identity matrix, the lambda equals 1 had multiplicity n, right? Because the polynomial that was the characteristic polynomial was equal to lambda minus 1 to the n. And we know that the eigenspace for this eigenvalue has n vectors for the n by n matrix. Now this is harder to check than the condition that the characteristic polynomial has distinct solutions, since we have actually to determine the eigenspaces, or at least find their dimensions.